So we've talked a bit about various running time optimizations of the basic Bellman-Ford algorithm. Now let's talk about optimizing the space required by the algorithm. To orient ourselves, let's just think about how much space is needed by the basic algorithm we've been studying thus far. Alright, so the correct answer here is the first one, A. The space required by the basic Bellman-Ford algorithm is quadratic in the number of vertices. It's theta of n squared. Why? Well, the space is dominated by the 2D array that we fill in, and there's only a constant amount of space per subproblem, and there's n squared subproblems. Remember, one index is the budget on how many edges we're allowed to use. I ranges from 0 to n minus 1, and then the other index is just the destination, and there's n of those. So in this video, we will talk about how you can do better, how you can get away with only linear space, not quadratic space. The initial observation is a simple one. Let's just return to the formula that we use to populate all of the entries of the array. So we always take a whole bunch of candidates. What are the candidates? Well, either we can inherit the solution from last iteration, I minus 1v, or we can choose something to be the last hop wv, and then we just paste together the best solution to w from last iteration, so ai minus 1w, plus we pay for the last hop the length of the edge wv. But here's the point. Staring at this formula, which subproblem values do we care about? Well, not that many of them. And in particular, the trait shared by all of the interesting candidates are they're all from the last iteration. The first index in everything on the right-hand side is always I minus 1. As a consequence, as soon as we've finished one batch of subproblems for some value of I, we've computed AIV for all V, we can throw out the results of all of the previous rounds of subproblems, AI minus 1, AI minus 2, and so on. All we need is the freshest batch, the most recent iteration, to correctly proceed. If we do that, the only subproblems we're keeping track of are the ones that we're filling in the current round I, and we're remembering the solutions from the previous round I minus 1. That means at any given moment in time, we're only keeping track of big O of n different subproblems. And this linear spacebound is even more impressive than it might appear at first, and that's because if you think about the responsibility of our algorithm in this problem, we have to output a linear number of things, right? We're not just outputting one number, we're outputting n numbers. Shortest path distance from S to every possible destination. So the space is really constant per statistic that we have to compute. One thing I'm not going to discuss explicitly, but I think would be a good exercise for you, go back to all of the other dynamic programming algorithms we've discussed, and of course by now there are many, and see which ones you can do a comparable optimization. Which subproblems do you need to keep around to compute the new ones? And if you throw out all the ones that you're not going to need anymore, what does that reduce the space to? For many of the problems that we've just studied, you're going to see a big improvement in the space required. So this would be a good time to pause and stop for a few seconds and think about possible negative consequences of this space optimization. So suppose we do this, either in the context of shortest paths, Bellman-Ford, or some other dynamic programming algorithm. We throw out the values of old subproblem solutions that we seemingly don't need anymore to push the recurrence further. Are there any drawbacks to this space optimization? So the answer depends. If all you care about is the value of an optimal solution and not the optimal solution itself, then you may as well just throw out all of these old subproblems that you don't need anymore to push the recurrence further. It's not going to hurt you at all. If, however, you want the optimal solution itself and not just its value, well, how did we actually accomplish that in the past? We had these reconstruction algorithms. How did the reconstruction algorithms work? You took the entire filled-in table and you traced backward through it. And each entry of the filled-in table, you looked at which of the candidates won, which comparison came out the winner when you filled in this entry. That told you a piece of what the optimal solution has to look like, and then you go backward through the table and repeat the process. If you've thrown out most of your filled-in table, how are you going to run this reconstruction algorithm? In the context of the Bellman-Ford algorithm, how are you going to reconstruct shortest paths if you haven't remembered all of the subproblems of all of the previous iterations? And you can certainly imagine in a routing application, for example, you don't just want to know that the shortest path has length 17, you want to know what route should we take to get from point A to point B. So in the rest of this video, I'm going to describe a solution for the Bellman-Ford algorithm. I'm going to show you how we can retain the constant space per vertex guarantee while recovering the ability to reconstruct shortest paths. So the idea is, for a given value of I and a given destination V, we're going to keep track of not just the one piece of information, the length of the shortest path from S to V that uses the most I edges, but also a second piece of information, which is the second to last vertex on such a path. So it's still going to be just constant space per subproblem. So we're going to call this second two-dimensional array B. We're going to call its entries predecessor pointers. Again, the semantics are this pointer points to the predecessor of this destination V on a shortest path from S to V that has the most I edges. Of course, if I is sufficiently small, there may be no such paths from S to V, and in that case, we just have a null predecessor pointer. So for a moment, let's just forget about the space optimization that we're trying to attain, and let's just observe that if we correctly computed these capital B's, then simply traversing predecessor pointers would reconstruct shortest paths. So why is this true? Well, two reasons that you've seen explain other things as well. So the first reason is, remember, we're assuming that the input graph has no negative cost cycle. Therefore, shortest paths have at most n-1 edges. Therefore, the b n-1 v's actually store in them the final hop of a shortest path period with no edge budget from S to V. So in the b n-1 v's, the final batch of predecessor pointers, if we correctly compute them, they are telling us the last hop on a shortest path to V. Now, the other part of the correctness comes from the optimal substructure lemma. So remember, way back when we started talking about shortest paths in their optimal substructure, we said, well, if only we had a little birdie which told us what the last hop of a shortest path was, then the shortest path would just be that last hop concatenated with a shortest path from S up to the penultimate vertex W. And these predecessor pointers are exactly this little birdie. We're storing at V what the last hop is, WV, and so we know that it's just that last hop with the shortest path back to S from W. And by traversing, that's exactly what you do. You just reconstruct the rest of the path apart from S to W. So if we correctly compute predecessor pointers, then they enable the simple reconstruction of shortest paths just by traversal after the fact. So that leaves us with the task of correctly computing these predecessor pointers. It's not hard. I think many of you could just fill in the details yourself, but let me just give a quick rundown. So remember, in general, we have this 2D array capital B. It's indexed by the edge budget I, and it's indexed by the destination V, and we're supposed to fill in BIV with the final hop on a shortest path from S to V that uses at most I edges. And if no such paths exist, then it's just null. For the base case, that's when I equals 0, and here everybody's predecessor pointer is null. So the way we're going to fill in the entry BIV is going to depend on which of the candidates won in the competition to be the shortest path for AIV. In essence, this predecessor pointer BIV is just caching the results of the competition we ran to find the shortest path for AIV. So to make this precise, let's just recall the formula that we used to compute AIV, given the solutions to the last batch of subproblems. Case 1 is when you inherit the solution from the last round, AI-1V. In addition, each possible choice for a last hop, W, V, furnishes another candidate for the optimal solution of this round. What you're going to pay the optimal solution to the subproblem I-1W plus the length of the edge WV. So we're going to fill in the BIV array basically just to reflect what happens when we computed the solution to AIV. In essence, what we're doing in the 2D array B is remembering the most recent vertex W that's responsible for furnishing a new shortest path from S to V. So in case 1, the boring case, where at iteration I we just inherit the solution from the last round, of course in the B entry we just inherit the last hop of the previous round. That is, if we use case 1 to fill in AIV, then we just set BIV to be BI-1V. So the interesting case is when AIV is filled in using case 2 of the formula. That is, when the shortest path from S to V suddenly improves given a budget of I hops as opposed to just I-1 hops. In that case, we're just going to cache the results of the brute force search that we did to evaluate the formula. That is, we just remember the choice of the penultimate vertex W that achieved the minimum in this round. Now notice that just like the formula that we used to populate the capital A array, the original array, to compute these BIVs, all we need to know is information from the last round, information from round I-1. So just like with the A array, we can throw out all of the predecessor pointers that date back before yesterday, before the previous round. Therefore, we again need only constant space per destination v to maintain both the shortest path distance from S to v with at most I hops and the predecessor pointer. So this is great. For input graphs that don't have negative cost cycles, we can not merely compute the shortest paths in constant space per destination, we can also compute the predecessor pointers in that same space, which allows the reconstruction of shortest paths. The one other thing you might want is to handle graphs that do have negative cost cycles. Now, in a separate video, we showed that just checking whether an input graph has a negative cost cycle or not is easily addressed by a simple extension of the Bellman-Ford algorithm. You tack on one extra iteration of the outer for loop, you let I range not just up to n-1, but all the way up to n, and if you see, for some destination v, an improvement in the extra iteration when I equals n, then that guarantees that there is a negative cost cycle, and it's if and only if. But in the same way you might want to actually have the shortest paths, not merely their value, you might want to actually have a negative cost cycle and not merely know that one exists. It turns out you can solve the reconstruction problem for negative cost cycles as well using the Bellman-Ford algorithm and predecessor pointers in exactly the way we've been maintaining them here. I'm not going to talk through all of the details of this solution. I'll leave it to you as a somewhat non-trivial exercise to think through how this really works. But the gist is as follows. So you run the Bellman-Ford algorithm, you maintain predecessor pointers as on this slide. And if the input graph does have a negative cost cycle, then at some iteration you will see a cycle amongst the predecessor pointers. Furthermore, that cycle of predecessor pointers must be a negative cost cycle of the original input graph. This means that detecting a negative cost cycle, if one exists, reduces to checking for a cycle in the predecessor pointers, which of course you can solve using depth first search at every iteration.